Our next speaker is Dr. Janet Bastiman, Chief Data Scientist for Napier AI, and in brief, what she's going to be talking about is rubbish data and how you deal with it. So, Janet, over to you.
So, hi everyone. I always like to start my talks with a bit of a rhetorical question. And in this case, how much would you spend for a successful AI project? And I also want you to think about how much money you'd waste before you realize that that project was going to be rubbish and unsuccessful. And the reason for this is that there are thousands of AI projects that fail regularly. I mean, there's probably far more than that, but there's a really bad example I want to start off with. So back in 2012, a hospital in the US, Memorial Sloan Kettering, announced this huge new project with IBM Watson. And they were going to create a personalized cancer care AI. It was going to ingest all the latest medical research, and it was going to provide patient-centric treatment. Really, really powerful thing. And both companies were hugely excited about this. And it was launched with a lot of fanfare. And then as the years went by, there were no updates. Until 2018, when the project was scrapped. And one of the doctors told the IBM execs that the product was just rubbish. They'd bought it with the hopes that it could achieve the vision that was sold, but it just couldn't be used for any of the use cases. It was recommending unsafe treatments. So, for example, they had a patient that had severe bleeding, and the drug that the AI recommended was going to cause that to worsen deeply. The cost of this failure was $62 million in just under 6 years. $10 million a year that could have been spent on literally anything else. And it's absolutely tragic. It's not isolated. And as I said, there are thousands of unsuccessful projects that hopefully aren't wasting as much money as this, but they're out there. But it doesn't need to be this way. And with a little bit of sensible actions, you can plan a successful project. Unless you've missed the hype around using artificial intelligence for everything, and particularly with the large language models that are out at the moment, you'll have been fed this story of identify the problem, gather some data, feed it into AI, mix it around a bit, and out will magically pop the solution. And this is the magic you're being asked to believe. And a lot of projects just follow this rinse and repeat without thought. And we're going to look at applying some scientific principles to this problem because there is a reason that it's called data science, because science is magic that works. But before we go into the detail about that, I just want to tell you a little bit about me. I've been coding for 4 decades. I did my PhD at the turn of the century, and I've been working on complex data problems for about 25 years. The past 15 of those have been at C-level. And I work with our customers to demystify AI. I'm chair of the Royal Statistical Society and AI section, and we work with the UK government, NPOs, and various other agencies to create standards and guidelines in AI. And I'm also part of the Financial Conduct Authority's Synthetic Data Expert Group. And my day job is a company called Napier AI, and we provide regulatory technology solutions for financial compliance. So we help the banks detect and prevent financial crime, which is an absolutely huge problem worldwide. As you can see, I love Lego, and I am remarkably easy to find across socials. I think I am the only Janet Bastiman worldwide. But let's get in, let's get into this. So no company sets out to fail ever. So let's dig what happened into that Watson example. That problem domain was really, really difficult. We're thinking 12 years ago, but ingesting medical papers and summarizing them accurately is still a problem. GPT-4 still struggles to do this for niche domains accurately. And recommending even non-personalized medical treatment is a hard problem. Combining the two, where you need that specialist domain knowledge, not only the papers, but generic medicine and all of that experience is really hard. They'd also not bothered with a risk analysis. So Where were their checkpoints in the project? They just went silent for years. They weren't doing any ethical checkpointing. They didn't check how the project was progressing, and they also didn't take into account some of the changes that could happen with the regulations. So, for example, the amount of patient data that they had access to was heavily restricted over the course of the project. They didn't get feedback from users, and this is critical. They didn't ask the doctors whether what they were doing was right. They didn't check whether the data that they were using, they were right. And this was kind of on the back of almost this wave of success they'd had off of Jeopardy, that they felt that they could achieve anything. And this is very common to a lot of AI teams. They believe that they can solve the problem. From a data point of view, as I said, they had limited data, and they jumped very early to synthetic data without checking it encapsulated the nuances of the problem. And this is really, really important. They'd gone to the wrong solution too quickly, and the models had learned incorrectly. They'd also only considered Watson as their technology choice. You know, they'd built it, so we're going to use it, rather than thinking about what would actually give ROI for the hospital. And then finally, there wasn't any trust in the system. There was no user feedback loop. All the doctors could say was that the output was wrong. They couldn't understand why Watson had come up with that. And if they had, then they may have been able to get suggestions for improvement. And each of these is probably a keynote in its own right, so I'm not going to go into them all. But I'm going to underline is that data piece, so failure 4. How can you assess whether you've got enough, whether it's good or not, and what you can do about it? So the first thing is, what is bad data? Because that's the key thing. And we can broadly define it as something that's not fit for purpose. But how can we say that something isn't actually fit for purpose? The first thing, is it inconsistent? So when you're trying to draw conclusions from the data, maybe it's just not reliable enough. It could be unbalanced. It could be something where your models will draw the wrong conclusions, so you really need to check that. Maybe it's inaccurate. Maybe just getting the wrong data. You know, one of my big bugbears, and it's a very trivial example, but if data's been pre-processed before you get hold of it, it may just be wrong. And back in the 80s, 90s, and early 2000s, for really bad companies, when you're gathering data for your database, your data admins would make some decisions which may seem sensible at the time to save memory. And simple things like, if you want to know gender, but you're only gathering title and you're not asking the question, then you extrapolate gender from title, which is fine if someone ticks the Mr. or Mrs. box. But for me, if you have a genderless title, what do you do with it? And I still get posts in 2024 addressed to Mr. Janet Bastiman, which is ridiculous. But you need to be aware that that data could be corrupted before it comes anywhere near you. You might have too few samples, and this is a huge problem. People always try and extrapolate from the data that they've got. They're building models, and they get an answer, but it's just not going to be accurate enough for the general population. You could also have gaps in your data, and those gaps could be absolutely critical depending on how you deal with them. So maybe it wasn't collected, maybe it's been removed from the data set for data privacy reasons, maybe you had a sensor error, or maybe the pipeline was broken that day. It could also be irrelevant. So you can throw in a huge amount of data, but it doesn't necessarily mean that you're going to get the right answer. Again, very trivial example of this, but when image recognition first came out, there was the famous problem of the background of the image being important to the classification. So huskies, for example, were not identified for any feature of the dog, just from the snowy background. So if you showed the image recognizer a dog with a snowy background, it would always say husky. So that background was irrelevant, but the network learned something it shouldn't have done. And then finally, it can just be poorly understood. So your own assumptions about the data can lead you to the wrong decisions. We are all biased based on our experience, and all of that information affects how we deal with data, what we believe to be true. So the first question that I am always asked by customers whenever they want an AI project is, how much data do I need? And it is a really difficult question to answer, because the answer is always, it depends. It depends on how much data you have available. It depends how confident you want to be in your answer, how representative your sample is, and what your beliefs about that sample is. So we can keep things really simple, and we can consider a single continuous variable. So something like height or salary. And we have a sample of the population in this room. How many of you would I need to measure, or our salary, in order to be confident that this is representative of, say, the UK population as a whole? So for height, I think we've probably got quite a nice distribution within this room, and it would probably be a pretty unbiased sample. But when you're talking about something like salary, just because of the nature of the industries we all work in, it might be biased and away from the population mean, and we need to be aware of that. But we've got a really good equation. This is pretty standard that you can look up. So if you're trying to estimate how many samples you need to decide, is it based on an infinite population or a subpopulation? And this is the equation for very large. The Z-score you can look up. It's based on the standard deviation. In this case, it's 1.96 for 95%, 5% error. Churn the handle, and you get about 385 people. And if you've got a completely random sample, that is enough to be 95% confident that for a mean, which is why we've got the 50% population proportion, then you'll be confident that the true mean lies somewhere within that. If you want 99% confidence, it's 700. And this is just for a single continuous variable with a binomial distribution. Now, if I was measuring the height at maybe a sports convention rather than in this room, even if I sampled correctly and I took 385, I'd probably end up with a biased sample. And you might be in that 1 in 20 where your calculated mean variance doesn't contain the true mean. Can you get away with fewer samples? Absolutely. How you're using the data and the variance in the population is really important. And as a rule of thumb, if you want to look at multivariate data, just raise the number to a power. Again, it's a very rough rule of thumb, but you can see the amount of data you need can expand quite quickly. The key here is to really understand what you're looking at, and most people just pick up data and throw it in the models and churn the handle without that key understanding. And you may be thinking, well, of course I wouldn't be daft enough to assume the height of the UK population from basketball players. But that's because you know that variable and that distribution. And the models we're looking at don't contain that information, they don't have that worldview. And it's reliant on you putting the data in to make those determinations. So think how often you use your personal bias in your day-to-day life and what that means for the data sets. And if you're looking at time series data, how far back do you need to go with your data? So here we're looking at the FTSE 500. This is from a couple of weeks ago. I've taken various different time periods. And as we go back through time, you can see that the patterns change considerably depending on those time windows. And we all know about some of the events, both nationally and internationally. I mean, you can see that big blip there in the 5-year look back that affect the pattern, but not all of them. And when you're looking at how much data you need for these time problems, you really need to look at, is that periodicity important? What are you looking at? What data is outlier data? And we'll come back to that in a minute. Are you looking for these normal peaks and troughs? And do you need to take into account regular time period events, so holidays, major sporting events, things like that? Again, The statistics here are a little bit more complicated than they were for just single variable sampling, but as a rule of thumb, look at least 3 to 5 times the multiple of the period you're looking at. So if you want to predict over a week, go back months. If you want to predict over a year, have 3 to 5 years data. And before we come back to that time series data problem, I just want you to think more about that data you're using. We're always told more data is good. So just keep throwing everything at it and keep stirring, just as the XKCD comic says, until you get the right results. Well, no. You've probably all heard that really twee saying that data is the new oil. Well, if we follow that analogy, and it is a fair one, we do not use crude oil straight from the ground. I don't know if any of you are F1 fans, but if you can imagine what the Monaco Grand Prix would have looked like if all the Formula One cars ran on crude oil, it doesn't matter how well engineered those vehicles are, the engines, the aerodynamic package, how skilled the driver is, those cars would have not made it round the laps. We use fractional distillation to get all the useful bits out of oil, and we use it all just in different ways. Do the same with your data. And I've got a great example here from earlier in my career. Please don't worry about trying to read this. Most of it will disappear in a minute. So earlier in my career, I worked for a company that did software for repair contracts for social housing. And the software itself didn't use any AI or machine learning models. It was far too early in my career for that. But they did want some analytics doing, which I did. They wanted to see if I could predict the parts and the skilled tradespeople that they might need over the course of the next year so that they could better pre-order what they needed. And this is a mocked example. I don't have access to the real data anymore, and even if I did, I shouldn't have extracted it from the system, so completely mocked for GDPR purposes. Now, if you were given this problem now, you might think you'd grab an LLM, throw it through that, try and summarize and extract the key fields. A lot of this information is completely irrelevant, and when they sent it to me, it came on multiple CDs, which was just a dump of their entire database. So this isn't even all of the information that I got. And it included transcripts of calls where the tenants might complain about multiple issues, which were all logged separately. It included feedback on various different tradespeople, not necessarily relating to the incident itself. And it was actually quite messy. It did, however, have the date of the original call, the date of the resolution, whether it was resolved, by whom, and any parts used, which was from a pick list. And as soon as it's from a pick list, that suddenly makes problems easy. So all we needed was that date, the resolution type, the parts and tradespeople, and that final date. And then we did a lookup to see, okay, well, this part is a plumbing part, or an electric part, or a cosmetic part. And 95% of the data could be removed. And it took this problem that was gigs and gigs of data nearly 20 years ago that was very difficult to understand into something that was very, very easy. Now, even though 90% of it was irrelevant for this problem, it was useful for other problems, and indeed we did a follow-up project looking at some of that other data. So you can distill your data, but document what you've done. What have you used? What were those assumptions that you used into the project so you can test it? Now, even within this data set, there were some huge outliers. There were several properties that had disproportionate number of calls, some that took over a year to resolve, and what do you do with them? So the first thing you need to understand is what you're looking at normal, or is it abnormal? And when you remove outliers, and this is a very, very simple example, you get better fit for the majority of your data. It really depends on what you're trying to predict and understand. Is it the majority, or do you also need to understand when those outliers happen? And this link at the bottom is an absolutely great blog post for identifying and dealing with outliers. For example, standard deviation from the mean, interquartile ranges, it's all very straightforward. it does have a huge impact on your models. So if you remove those extreme values, you need to understand the impact of that. So if we go back to the FTSE 500, COVID was an obvious blip, and you might think you'd want to remove that as an outlier. But if we look back further from 10 years, so this is the 30-year look back, there are multiple big drops. Do we want to predict these sorts of unusual events? Do we want to anticipate them happening? Or do we just want to predict normality and then alert for when it's deviating? You really need to understand whether these are outliers or something important to you. And this is one of my favourite scenes from Day After Tomorrow. I'm probably one of the few people that has this as their favourite scene, but it's where the scientists are seeing the odd measurements in the sea temperature. And the first time they get an odd measurement, it's just ignored and the alert's switched off. It's an outlier. But when they start to see more odd events, they realise that it's actually something real that they're observing. It's not outlier data. And there's real science behind this. This is a very interesting paper on oceanic temperature drops. And when you look at those observations of wave heights and temperature, they use 3 different measurement techniques in order to account for errors, which can vary by seasonality and different geopositioning. And why it's interesting is it shows the effort that needs to go into detection and quantification of errors in the data gathering stage. And this is something that we all need to remember. We take data sets and we assume that they're okay, and we need to take that step back and actually ask those questions about what happened before. But what if your detectors fail and you're missing data? We get gaps. And what you do with them, you really need to think about whether that data should exist or not, and the impact of assigning it value. So is the data missing for a reason? Is it that faulty detector? Is it a failure to answer a question in a survey? Is it random or correlated with other features? There is a lot of analysis to be done up front. So if you had a data set and it was missing transactions in a day, that might be completely normal. I don't spend every day. But if it was maybe the data coming from the toll booth on the M6, then you might think, oh, maybe that's a failure in the data being sent to us. For health data or anything supercritical, you need to be really, really careful. Assuming a patient's blood pressure as an average of surrounding results, or even assuming it's normal because it wasn't tested, is really dangerous. And you'll probably need to avoid using that data for those models. And there are plenty of techniques that you can use. And again, there's a great example at KD Nuggets of how to fill your data. So you could fill it with zeros, you could do mean fills, variance around the mean, random between min and max, things like that. But you do really need to understand the impact of the methods you use on the accuracy of your models. And again, here's a graph from a paper looking at network models. So a lot more complicated, but I love this because it does show all these differences. So in this case, they had 6 different methods of removing data, which is across the top. They had between 10 and 50% data removed, and then 5 different network techniques, which are this bit down the side. They did this on both a 30 and 80 node network and used 2 different techniques to fill the gaps. The key here is that when they looked at the deviation from the network when it was complete, different techniques on different sizes and different treatments gave them different results. So you really need to think hard about what techniques you use to fill the data, because it will impact your end results. It's really quite important. But starting to generate some of this data is the next step on how to deal with some small data sets. And sometimes you just don't have enough to do anything with. Particularly medical data. One of my team, as part of his PhD, he was looking at spinal discs, and he only had, I think, 12 or so spines as images to look at. But what he realised was he didn't need to train on a whole spine. He was just looking at discs. So he could chop that image up and immediately got an order of magnitude in terms of the amount of data that he'd got. So you need to be clever with your data. But if that doesn't work, synthetic data can be your friend. Now, synthetic data, it can give you that privacy support, so you're not using the real data. It can be near infinite, which is very, very useful. And if you do it properly, it will be unbiased. It allows you to test and develop in situations where you can't get that real data, particularly where you can't remove it from client systems. And this is one of my problems in my day job, is that banking financial data can't be removed from systems. So when we're making our models, we need to create synthetic copies. And this is where we need to ensure it's got the same shape as real data, so the same statistics, the same correlations and interdependencies. You can't just generate randomness, or you'll learn nothing, or at best your models will learn the wrong things. If you don't have any real data to start with, then you're making it up again from your bias, which is a huge problem. And the more data you have as a starting point, the more likely you are to encapsulate those real statistical issues. So if we think back to earlier on, ideally you'd have those 385 samples, but if not, work with what you've got, but you need to test it. You might need to impose some rules on your data. I've seen an awful lot of synthetic data where simple things like dates or ages or salaries can sometimes be negative, which is going to cause interesting problems in your models. But it is critical to document all of your assumptions so that when you're doing that test, you know what you assumed up front. And GPT has been brilliant here. Loads of data scientists are using it to mock data. Again, there's a really nice article on Medium just showing how to do this. It's very easy to search for. And you may find that actually creating the code is easier. ChatGPT can do this for you as well, and then you can download that and tweak it so that it fits your requirements. This is a really interesting example because it kind of overhypes some of the benefits of using GPT to create synthetic data. So in this experiment, you had a very small sample of data and various techniques to create generated data as multiples of that, up to 32 times synthetic to every real data, apart from the line that performs well, which is the brown line at the top, which was using no real data at all. And this paper was outed as, you don't even need real data, just use synthetic. The problem was that the problem domain was positive and negative film reviews, of which there are a huge sample in the training set. So, of course, it's going to be able to generate really good, realistic examples, far more than restricted to the trivial real samples that it was given with a zero shot. Be cautious. It's one of those things that if you just assume it's going to be right, then you will have problems and your data will be bad. Now, if you can't take those real samples off and you can't use a public cloud GPT, you have to do your own thing. There's a great paper there that shows you how to do everything from scratch, create your own GAN, create your own procedural networks. It's possible, it's something we have to do because we have to generate synthetic data from our customers' data within their environment, so we're only taking the synthetic data off. Again, the key thing's testing. Especially if you're in a restricted environment, test that your synthetic data matches your real data before you take it off and use it. A lot of people, when they're using synthetic data, they test it against their real data, they don't get great results, and they will make excuses as to why that very small sample doesn't get great results, because it's a small sample, and it'll get pushed to production so that they can gather some more data. This can be really dangerous because you're then using those poor models to make real-world predictions, which is never a good idea. Testing is absolutely critical to data science. And talking about bad data is one thing, but if you're in a business environment, you're not isolated. I think the blurb of my talk included how to manage stakeholders. So I think as my last little anecdote, I want to tell you about something that happened to me earlier in my career. It's really hard if you're asked to do something that isn't great, and until you're at a level where you can say no, you may be forced to as a data scientist. It's really difficult as it depends on the statistical literacy of your management team. In an ideal world, they all would be. In the real world, they tend not to be. And in that ideal world, the conversation should go a little bit like this. You know, you express concern about a project, you say it's unethical, your boss, who's lovely, is, you know, very accepting of this, asks what you need, and you say, I'll try something else. That would be lovely. What normally happens is something along these lines. You come with the same concern, and you're told it's not your problem. Just do it. We'll find a way around it. And it doesn't matter how much you say it could be dangerous. You get something along these lines. Do it, or I'll find someone who will. That passive-aggressive, you might be first out the door next time we have to do redundancies. Now, maybe it falls somewhere between these two, but in my experience, it's far more towards this second example than the first one. If you are a stakeholder and your data person is expressing concerns, please listen to them, particularly if it's a business critical project. They are expressing concerns for a reason. It's not because they're incapable, it's because they have bad data. And bad results are never good for a company. And if you're the data person, this is always going to be a difficult conversation, and you're always going to approach it tentatively, but provide the evidence. So one of my previous jobs, the CTO was absolutely dog crazy. He'd done a Tough Mudder event at the weekend and noticed that social media was absolutely flooded with dogs in headbands. And we were a marketing company, and he told me to drop everything and build a new classifier that could pick out these dogs in headbands so that we could sell it as a solution to Tough Mudder as an events company. Now, I had a look, and I just couldn't see it. I had a quick skim over the social media, and obviously that was me doing my job wrong. And it didn't matter how much I complained. It literally got to that point where he told me that I wasn't capable. And I have a certain reaction when someone tells me I'm not capable of something that I know that I can do. It makes me quite angry, but it also gets me very motivated. And I have had managers in the past that are aware of this and do it deliberately, but they will all be chapters in my memoir when I get around to writing it. But in this instance, there was only one thing I could do, which was channel my inner Mark Watney at the time and data science the shit out of it, which is what I did. So, at the time, over 5,000 posts across socials, Instagram and Twitter as it was then, with all of the Tough Mudder events that had happened that year. So that's a reasonable data set. It's far in excess of what we had at the beginning. And we had paid access to the Twitter Firehose and the same for Instagram. So I could get all of that data. That was like a 2-second job. I used an off-the-shelf object detector to try and work out, you know, which of those images had what in, and got all the ones that said they had an animal in, which was 513, so under 10% of those images. And I thought, maybe he has something. Most of them were actually dogs as well. So I was feeling, like, okay, maybe I'm wrong. Maybe my bias, being a cat person, meant I just couldn't see them. But I didn't at this point have a detector for Tough Mudder headbands, because that was the thing I was trying to avoid doing, because I thought it was a silly idea. And given there was only 500, you know, there's another great XKCD comic about the trade-off between automating and doing things manually. But for 500 images, I just thought, I'm just going to go through them manually. So I did. And I found 17 out of that entire 5,320, 17 images had pets with headbands. 13 were dogs. 3 were cats and a possum. There were actually more pictures of babies in headbands than there were dogs, but he just couldn't see this. And even when I presented this back to him, I'd done my job wrong, I hadn't done it properly. And in the end, I just had to say, show me. He couldn't find more than 5 examples, whereas I'd got 13. And he was convinced that someone must have deleted them and went off in a huff. However, so the only way you can manage stakeholders really that don't trust your word is just demonstrate it, get the data, show it, tell the story, show them the worst results. This is a very, very trivial example to do with marketing. Imagine if this had been a medical healthcare product. Imagine if this had been something that was maybe deciding whether someone had committed fraud or was requiring or could get a mortgage. A lot of the things that we're working on have real world impacts. You need to make sure it's right. Show them whether it can be done or not, what you need to fix it, or whether it just can't be done. So I promised you some key takeaways. What does good data look like? Large amounts, relevant, representative, so correctly sampled, right recency, high quality data with that known provenance. Remember, you might need to double check how the data was collected. Yes, you can get away with less. Test it, make sure you know what the risks are and document them. Get rid of that irrelevant data because it's really going to mess up your project. You will learn the wrong things and potentially give some really bad results. Do that analysis. Before you commit to doing any model, make sure you've got the right thing. It's absolutely critical. Synthetic data can help, but again, use with caution, make sure it's right, make sure it matches your prep work. And then finally, be honest to your stakeholders. Don't string them along. Establish that trust and tell them when things can't be done. If you cannot explain data to a non-data person, learn, or you're going to spend your entire career frustrated. There we go. So, thank you very much.
Our next speaker is going to be in here at 11 o'clock. Well, I think we've got time for a quick question, to be honest. Has anybody got anything from the floor? If not, there's just one question I want to ask, and it's, if I'm not an industry insider here, this is not my field at all. Why, in the name of the wee man, would you proceed at all if you know you don't have enough data?
It's really difficult. A lot of the time it's pressure. Most businesses are rushing to get something out, and it's work with what you've got, we'll get more. So you get pressured into starting something, and then that extra data never comes. So you just end up building something, and then it gets pushed to production. Saying no to a senior person in company is, takes an awful lot of gumption. And depending on how senior you are and how replaceable you feel you are, it can be really difficult. So a lot of people do things that they don't want to do just to keep their jobs. And that's a real problem in the industry.
Thank you very much. Janet, thank you very much.